I'm Stephen Foskett. Welcome to Tech Field Day, coming to you November 2016 from Silicon Valley. We're here with StorageOS and the delegates that we've brought in from around the world. These are folks who specialize in servers, storage, networking, and they are intending to be part of the discussion that you're about to see. If you'd like to learn more about Tech Field Day, come to techfieldday.com. And if you'd like to see more videos like this, just go to youtube.com/techfieldday.
Hello, my name is Alex Chircop. I'm the CTO and founder of StorageOS. And in this session, we're going to cover the typical use cases for StorageOS and give a high-level overview of the architecture and the components within StorageOS. So just to set the scene, in our previous discussion, we talked about how StorageOS runs as a container within an operating system as opposed to being a standalone storage system. So today, I guess most users in data centers that have infrastructure storage have a number of nodes that run their applications, and they may connect to some storage. I'm going to turn around this way if that's okay. And they'll have some sort of storage area network in their system for the applications to access the storage. And I guess over the last couple of years, we've kind of evolved to a state where we have servers that, rather than have dedicated storage, they have hypervisors, and perhaps they have applications running as VMs within those nodes, and they might have some sort of storage system that runs as a VM within those nodes. And the application can access the different storage systems. But again, those storage systems are running in their own instance, with their own operating system as a separate VM. In the StorageOS case, if you can, I'm going to draw a slightly larger server now. We have a bunch of computer resources. So we have a CPU, we have some memory, and we have some disk, and we have some network. And this can obviously be bare metal, or it could be a virtual machine. And in that server, you're running an OS. And that OS is got the functionality to run containers. So we now start up a bunch of containers within our system, running our application. And we also run StorageOS as a container within the same operating system. So the picture that I'm trying to draw here is that StorageOS just really is another Docker container running alongside any of your other applications, and it accesses the same resources that are available to the nodes on the box. Simon, could you just quickly show our Docker containers running on a
Sure.
cluster?
Okay, so on this node, this is the same node that I was giving the demo on a few minutes ago. If I just look for the StorageOS containers, OS, so you can see that I've got a couple of containers running here. So I've got the control plane container, which is this one here, and the data plane container. So those Docker images, grab. So if just to show the container, the image itself. So you can see that our containers are sort of 70 megs some depending on the features enabled in them.
So it literally is a tiny container that you can just install anywhere that you can run a container environment. Today we are running on the Linux platforms, but we're also working to create containers for other platforms, including Windows and macOS as well. So as we saw there, it's one container, and it can run in a number of different modes. So in the first instance, we have the control plane. The control plane is what manages the configuration and the management of the various components within the data plane. So the control plane accepts requests, manages the environment, discovers the environment, and in general allows you to apply config changes with APIs. So we have an API server here, which is completely RESTful. On top of the API, we have a CLI, which just runs commands directly against the API. And we also have the GUI that Simon demonstrated earlier, which again is, some storage providers might say this in that they have a GUI which controls an API. In our case, everything that you do in StorageOS is entirely API driven, and the GUI really is just a wrapper around those APIs to give you a bit of ease of use. But effectively, everything you see in the GUI or everything you can do in the GUI, you can also do directly with the API. The idea being that most users may be integrating this into some sort of orchestration mechanism, into different schedulers like Kubernetes, and the API is the main interface of how you control the system.
That gives a lot of reassurance, because it means there's nothing you can't do in the API that you can do in the GUI.
That's literally correct. I mean, the GUI really just calls API RESTful calls directly.
Forgive me if I missed it, but does that GUI run in every StorageOS container, so the management plane is distributed too, or do you run like a separate container to do the management of?
So there's a single container that has a single binary within it. That binary, depending on the flags that you give it, will run either the control plane, the data plane, or our client mode, client-only mode.
Okay.
So when you run the control plane, the UI and the API and some of the messaging and all those components that Alex will go into detail, they're all baked into this one image, into this one binary. So
you just tell it which one you want it to be when you initiate it.
Yeah.
Exactly. So typically, most of our users, because the overhead is fairly small, just start up the control plane on all of the nodes, and that means they have access to the API and the GUI from any of the nodes. So the interesting thing about the control plane is we've tried to make it easy for a user to configure and set up StorageOS. So one of the issues that we very often come across when users are setting up software-defined storage is it can be fairly complex. People need to define partitions, disks, maybe hex IDs, or complicated LUN paths, and this sort of thing. So one of the key things that the control plane is responsible for is discovery. So using a number of plugins that reach out of the container, we permission the container to access the services that are available in that operating system. We can identify the file systems, we can identify disks, we can identify LUNs that are presented in to the environment, and this allows us to very easily do the right thing for the user without the user having to work out a lot of the sort of hard stuff for themselves. The API, sorry, the control plane also has the rules base, which provides the automation that Simon demoed earlier. So the rules base allows StorageOS to automatically evaluate the labels against the clients, the disk volumes, the applications, the API calls, and automatically apply data services and placement based on those rules. And then finally, the most important thing, I guess, is the scheduler. So in the control plane, we have our own scheduler, and that is effectively what manages the configuration and tracks the availability and of the environment, such that we take the configuration that is requested by the user, whether those are API calls or whether it's automated stuff from the rule base, and we implement those. We implement the required state in the environment out of that configuration. As we said earlier, we manage our config through KeyValueStore. Oops. The KeyValueStore, we've abstracted out the different options for the KeyValueStore, so you're free to use console from HashiCorp or etcd from CoreOS or Zookeeper from the Apache Foundation. Any one of those works particularly well. But KeyValueStore can coexist with the control plane container with the StorageOS install, or it can be separate nodes in the environment. In smaller systems, we tend to see our customers deploy the KeyValueStore alongside our containers because, again, it's fairly low overhead for the use that we're making of it. But in larger environments, they typically already have some sort of KeyValueStore which they're using for perhaps service discovery or for something like Kubernetes in their environment. And finally, we have an integration layer on top. So the control plane is also responsible for doing the tight integration with the different container runtimes and the schedulers that we're supporting today. So today we have integration with Docker, Swarm, and Kubernetes. So effectively, when a user executes a Docker run command, that is actually in generating an API call into our Docker plugin, which integrates directly into the control plane. So effectively, the users can now just use their traditional schedulers or traditional Swarm commands or traditional Docker run commands and not actually have to worry about whether they have to provision a volume up front or what type of characteristics they have to apply to that volume, because the rules base automatically applies the correct data placement and data services based on the labels that are linked to that application.
So as this starts to kind of like scale out and you get more and more nodes and more drives and so on and so forth, how do you guys deal with hotspots in the storage?
So we are working on sort of threshold analysis for both I/O rates and throughput, and we will attempt to move things around based on that information. But that's a feature that we're looking at probably mid next year. Right.
So as latency starts to spike on an individual one, you'll start to move stuff
Correct.
into the background.
Yeah. So it's probably worth noting that you can have because you have a very distributed environment with your containers, and you may not need to have sort of tens of terabytes per node or whatever. The amount of storage and the amount of I/O that each container needs can be fairly manageable. So in environments where you have relatively fast disks with commodity SSDs, etc., you may find that actually you don't have a lot of those hotspots anymore because the load is necessarily distributed as opposed to sort of focused on perhaps a traditional 2-node storage array, for example.
And because you're running the StorageOS container on the same of each of your compute nodes as your application containers, then are they generally doing most reads and writes locally and then one replica elsewhere? So actually you're kind of segregating your I/O by the number of nodes as well?
That's exactly it. So most obviously there are exceptions, but most workloads that we see are reads intensive as opposed to write intensive. There are the obvious exceptions, but what that basically means is that the containers are going to be running really fast with their reads, accessing local SSDs, and the only thing that actually goes out of the network is the replication traffic. Okay.
The replication traffic's being handled by the container, not the underlying storage.
The replication traffic is being handled by the container, correct. So that takes us neatly on to how do we handle data.
So you've got data for replication going across the data plane, and then you've got your front-end application traffic. So, and I'm assuming you're mounting some of that storage from the other application containers, or the other application containers are mounting from StorageOS.
Yeah.
So are you able to attach those StorageOS containers to multiple subnets so that you've then got segregated traffic? Or are they sharing? Are your applications and your data all sharing the same network?
No. So because we live in a container, you can operate in a number of modes. We can operate in a host networking mode where we're using the raw networking that's in that operating system instance, but we can also use whatever your choice of network overlay in Docker is, whether that's Weave or any of the, Project Calico or any of the CNI type solutions that are out there.
You could tie into multiple Linux bridges and have separate access to each one if you wanted.
Absolutely, and to coin a phrase, containers do microsegmentation pretty well.
Are you writing all that data to replicas and then acknowledging back to the original, or do you wait till it just writes to a local node and then it'll replicate after the fact?
So replication is handled synchronously within a cluster, because we kind of make the assumption that eventual consistency is bad if you're running databases or those sorts of things in our environment. We wanted to get the same level of sort of crash consistent recovery that you get with a traditional storage system. So within the cluster, we force it to be synchronous.
Okay.
I guess at some point we may offer asynchronous, but that's really not recommended. When we replicate between clusters, then we can do both asynchronous or synchronous, depending on your, RPO type, RTO type objectives.
Is that the number of replicas within a cluster? Is that configurable? And can you do, say, erasure coding across that cluster?
Yep. It's fine. This is a really good discussion. I like it being interactive. We were going to have a separate section all about durability and high availability.
Oh, okay.
But just to answer that question, we do erasure coding within a node so that we protect against disk failures. And we do replicas to protect against node failures. You can obviously have one or more replicas depending on your levels of paranoia or the sort of distribution of your cluster and your data center. However, we also thought it was important to have reliability at the disk level, because when in many systems we kind of saw that replicas happen, but then you have the equivalent of RAID 0 on an individual node. So if a node fails and a disk happens to fail at another node, then sometimes you lose data, which is obviously undesirable. So we thought it was important to protect against the actual data within a node as well, and that's where we use erasure coding. And the reason we use erasure coding is to be able to provide multiple levels of resiliency. So effectively, you're obviously all familiar with RAID 5 and RAID 6, but with, in some environments we find our users are looking at really large disks like, the 8 terabytes and the 10 terabyte drives, and rebuild times for those systems can be ridiculous. So it really is important to have more than single or dual parity, and using erasure coding allows us to have as many parity disks as you want.
So do you have a typical recommended, for if you're doing a physical environment then, what's the minimum you would say to a customer they need to do to be able to do enough, have enough drives in their node to do erasure coding to a sufficient level, like 5+2 or whatever?
It's a really simple statistical question, right? So you want to look at the odds of a disk failing while a disk is rebuilding. We kind of optimize this a little bit because we have logical layouts across the drives. So erasure coding allows us to recover only the data that was written. So if your drives are only half full, you're only recovering half the drive. But effectively, it really is a simple statistical question. If you have very small drives or very fast drives that can rebuild easily, you can have less parity. And if you have really slow drives or really large drives, then you need more parity. And we don't have a specific recommendation. It really is up to you. We're going to come up with some recommendations based on what we see people doing in the field, but we don't have a hard and fast rule.
But it really is a storage array. So you have, if you're doing erasure coding across local drives and so on, you've built a storage array.
We have.
So what other components of the storage array do you have? Do you have caching? Do you have, tiering? Do you have other acceleration and all that sort of thing?
So we talked about the control plane. Obviously, a lot of the questions we've just been talking about are all to do with the data plane and how we manage the data path within our environment. So I'm going to start off by drawing a really big box. And this is our data plane. And the data plane contains a number of components. We have our config, which is a little system here. And that config is the config that is the actual active config that our nice control plane with our scheduler has kindly generated based on the placement rules, the data policy rules, the data services that need to be configured, etc. We thought it was important that the data plane is accessible through the largest possible variety of media, because we didn't want to restrict what the data plane could present to. So clearly we wanted to do the basic stuff like iSCSI, because that's what a lot of people do today. However, what we also discovered is that in a lot of systems, iSCSI can be relatively complicated. It's really hard to secure. If you've ever tried to do IPsec with iSCSI, you know what I mean. So we decided to write our own direct protocol as well. The direct protocol allows access to the volumes in the data plane, and it's this protocol that we use when we're presenting volumes out to other nodes in a StorageOS cluster, or even when we're presenting storage out to client systems that are connecting into StorageOS using our container. So it effectively gives us an easy way of implementing a storage transport without the complexity of setting up iSCSI initiators on every operating system, et cetera, which can be tedious and not necessarily very scalable when you're running dynamic containers in a scheduled environment. And finally, we also have what we call our volume file system. So local to each node, we expose, I guess, an abstraction of the volume such that other containers within that node can access the volumes directly. So we have under the operating system where StorageOS is running, we'll have a /StorageOS/volumes, and we'll have a bunch of volumes in there that match the volumes that have been created on the different nodes. So that's it. That is how we do presentation. Once we sort of receive data, we receive I/O requests, we receive control requests. We have a number of storage primitives. And by this, we do things like our replication, our transaction logs, and, following on from your question, Stephen, our caching. So effectively, we provide a standard set of storage primitives that we can apply to the volumes that are being presented by the data plane, such that any type of volume can be replicated, irrelevant of the protocol that it's coming in on or the way it's being presented. We apply transaction logs. Now, the reason why we apply transaction logs is because we have to remember StorageOS doesn't have any proprietary kernel modules. It doesn't require you to recompile your Linux kernel. It doesn't require you to have NVRAM cards or any sort of proprietary hardware. So effectively, we have to make sure that the writes that are coming in are stored durably. So we use a transaction log, which is also synchronously replicated to other nodes in the system. So think of the transaction log as the write-ahead log in a standard database. Effectively, the I/O that's coming in is protected against, say, a node rebooting or a node failure that happens before the I/O has actually been persisted to the back end. Does that make sense?
Yeah, but the data is not going to be committed until it's on 2 nodes.
Correct.
Okay. So it'll be in the transaction log on 2 nodes, basically.
Correct. So you get an acknowledgement back once the data has been committed to 2 nodes.
Right. Okay.
We have the option to do the transaction log in memory, or using any combination of disk that's available on the system. If you have something like NVMe drives or SSDs, that will make a lot of sense to use for the transaction log. But
if you're using, say, 3 replicas, does it acknowledge after the second or after all 3?
At the moment, for the transaction log, it will acknowledge only after all replicas. So we're kind of a little paranoid with database integrity.
Of course we're paranoid.
Yeah, well, that and I've done storage for 25 years, and you after your first 3 a.m. call, you kind of know what works and what doesn't work, and make sure it never happens again. So similarly, another primitive that we adopt is obviously caching. We can use memory within the system as a cache. We can also use any fast media that you've got in your box as a cache. So typically users have maybe a mix of storage in their boxes. A lot of the use cases we come across today, funnily enough, are where users are deploying entirely SSD type solutions, so that's less relevant. But there are still a lot of use cases where people have a mix of, say, SSD and standard storage, or they have a mixture of different speeds of SSD. So more and more what we're seeing nowadays is maybe you'd have like a highly durable, long lifetime NVMe card in the box, and you might have perhaps lower durability Archive Plus type SSD for the majority of the capacity.
Whether you're doing all this deduplication and compression, so that's going to help the SSD piece. Just out of interest, what happens from a licensing perspective when you hit your license limit for capacity? How does that work?
It's really simple. We just stop you from making changes. So we don't stop the data traveling on the box, but you can no longer provision any more volumes. You can't create new replicas. The system kind of goes into stasis until you go below or you upgrade your license. So the idea is we don't want people to dramatically exceed their license and then suddenly find that their data has gone away, because that would be bad. But on the flip side, we want to strongly motivate you to upgrade your license at that point.
So the volumes you already have presented have a set size associated with them. So you can continue to read and write normally to those. You just can't present more volumes.
Correct.
Okay. Sorry, for a second there, I thought you meant like all my writes were going to stop. I was panicking.
No.
They're going to freeze off all the rights. Yeah. Sorry, you didn't want to write. You know?
Yeah. So we wouldn't want a licensing snafu to affect a user, because generally users don't go over their licenses intentionally.
Now, is there any QoS or anything for multiple containers running on the same node?
Today we implement a fairly basic QoS, which effectively acts as a throttle, and it's controlled by the rule space, and it allows you to set different priorities for different containers based on their labels. So you can say, these are my fast containers and these are my slow containers, and the slow containers get less access to resources than your fast ones. In the future, we're planning to have a much more fine-grained QoS system, and that's going to be built into the Enterprise Edition.
So everything really maps back to those labels.
Exactly. So those are the primitives that we apply. We then have what we call creatively named data services. So by data services, we're talking about We're talking about how we protect data, and that includes the erasure coding and the volume replicas. And we also provide our data reduction. And that is compression and dedupe. So the idea here is that you want to protect your data. We've already talked about erasure coding within a node to protect against disk failures. We talked about replicas to protect against erasure coding for disk failures, replicas for node failures. We also put a lot of work into our compression and dedupe algorithms. So the idea here is we thought that actually disk still remains expensive. People want to use SSDs for more and more workloads, but obviously to use SSDs effectively or cost effectively, you do need to do deduplication and you do need to do some sort of compression. it's not good enough to have one or the other, because dedupe works better against loads where you're running multiple instances of the same application, whereas compression tends to work better for when you're storing data, say for example from databases or that sort of thing, which doesn't tend to dedupe as well. So it was important to have both. We also thought it was really important not to have to give the user the decision of where and what they apply data reduction to. So as you saw in the demo, we look to just enable compression everywhere, mainly because compression has, apart from the nice feature of reducing the amount of data that you need to store, it also has the side effect of generating less bandwidth on the back-end disks and using less IOs to store the same amount of data. But we also were fully aware that users don't often know whether the data that they're going to be storing is going to be compressible or uncompressible, and what type of data they're going to be storing in a volume. So very often, especially if you're just creating a file system which is going to be used by one or more applications, you don't know if it's going to be nice compressible HTML and CSS, for example, from a website, or whether it's going to be uncompressible stuff like images or video, for example, from some other system. So what we did was we created an algorithm where the compression is applied dynamically based on the content of the data blocks themselves. And if a data block is compressible, it will get compressed, and it will be stored in a compressed format. And if the data block isn't compressible, we stop wasting time with the data compression algorithm for that particular data block and just store an uncompressed block. This has the advantage that even if you have compression switched on for your volume, you can write completely uncompressible data into that volume and not create either a CPU overhead or not expand the size of your data as it goes through the compression algorithm. This also means that you can dynamically flip the labels that switch those features on or off completely dynamically within your system. So for example, if you created your volume and you didn't have compression enabled, but halfway through using it you said, oh, actually perhaps it should be compressed, you can flip compression on at that point in time, and the data blocks will get compressed at that point in time, from that point onwards. It also means that if you've deployed a system with compression and you've discovered, oh, my CPU overhead is too high or my apps need more CPU bandwidth, you can switch compression off and get your CPU resources back. So finally, we also have, this is also where we do our encryption. So the data plane manages a number of cryptographic functions, both for data at rest and data that is going over the wire. We use this feature to provide users the ability to switch encryption on completely dynamically based on their requirements for their data. This means that they can switch encryption on, for example, if they're using third-party service providers, or perhaps if they're running in the cloud. Remember, StorageOS runs anywhere you can run your containers, so you can use this feature, for example, to apply compression and encryption to all the data that you store in EBS volumes in Amazon. The encryption is based on a key management system that's handled by the control plane. And what this allows you to do is to effectively apply keys to the encryption that only you are aware of. So this gives you secure encryption in transit and at rest without your service provider or your third-party vendor having access to your data.
Can you plug in or replace that functionality with, say, a third-party HSM or anything like that? So if you're already utilizing that anyway?
Very good question. Every single one of these data services, although I haven't quite drawn it this way for simplicity, is actually a pluggable module. So any of those systems can be switched on or off and added to the data part transparently in the data plane. So when you're doing if you don't want encryption, for example, you actually have no overhead of the encryption engine because it's not even in the part. Finally, for the with regards to the data plane, finally, the last thing I want to talk about is we also, in the same way that we virtualize the front-end presentation, we also virtualize the back-end presentation, or the back-end persistence, I mean. So today, we can use one or more file systems to persist on. We can use one or more disks to persist on, or we can use any type of object store. We're compatible with S3 today, but looking to add compatibility for other standards later on. So the idea here is that you can create a volume, and the data for that volume can be mixed on a number of different disk devices which are available in your system. So you install the data plane with the control plane on a number of nodes. We discover the storage that's available on those nodes, whether it's physical drives or virtual drives or EBS volumes or file systems that are available to you or object stores that are available within your environment. And we create a pool of capacity out of all of that. And then we handle the replication, the erasure coding, and all the data services across that pool to transparently give you volumes that you can consume from your control plane.
So, if I'm getting this straight, so you can use, for example, S3 as a backing store for block storage for a database?
Absolutely, if you wanted to.
So can you totally mix and match any of these backing stores that you mentioned?
Absolutely.
Can you have multiple ones in the same volume?
Today we're mixing the caching capability and the transaction log capability between different data pools or between different backends. So, for example, you could have, say, if your database was an archive database, you could have your database sitting in S3, but have caching in SSD and your transaction logs in SSD to kind of give you better transactional throughput for the hot data that you're using. In the future, we'll probably look to have a better mix. But to be completely honest, we often see tiering as a very complicated solution and one that many users don't often get right. They often hit lots of unexplained performance issues when they implement tiering badly. So it's not something we're prioritizing at this stage.
Okay, so you're caching, but you're not yet tiering, really.
Correct.
And I presume that the policies that we saw earlier, that Simon demonstrated earlier, would keep us from doing really dumb things like putting a high transaction database on remote S3 storage or something like that.
Oh, absolutely. You can actually set up the rule base to say, for example, my production databases go onto SSDs and my development systems go into slower media. But you can also do much more complex stuff. You can say your production Postgres databases in London get replicated to your data center in Frankfurt and have these set of encryption keys applied, whereas your development environment always gets located in Amazon and only has snapshots applied, for example.
That's actually incredibly powerful, what you're describing.
Like to think so.
I think that, just to let me translate the storage for those of you who are anti-storage. What he's describing is what storage companies have been trying to do for a couple of decades. And doing that is really an incredibly powerful addition to the IT arsenal, not to mention the container arsenal.
We think so. And the thing is, it becomes much more important when you have a more dynamic environment with microservices. These aren't set up and forget environments. They're environments that change and adapt all the time. So you do need an automation on policy to get things right. Otherwise, you'll be chasing your tail all the time.